Welcome back, everyone. Today, we're going to talk about relations, and we're going to talk about some properties of relations, go through what relations are. Earlier in the term, we gave an expression of a definition of what relations are. We're going to go into a little bit more in depth with that definition, and we're also going to take a look at some properties, some special properties about relations, take a look about partial orders, uh, equivalence relations. And then finally, we're going to end off this section by looking into this thing called the growth of functions in big O notation. Now, I do want to give you the extra information that the last topic here, the growth of functions in big O notation, really should belong in the functions section, but I decided to push it until this section. So just take note of that. It is more related to functions than it is with relations. All right, so let's begin. The definition of a relation is a subset of A cross B. Now, this is a definition that we gave before earlier in the course, but anytime we're talking about a relation, we're always talking about two sets, okay? Whether we're talking about A cross B, or we may be talking about A cross A in the case where we say it's a relation on A. If we say this is a relation on A, what we typically mean is that there is a relation that is from A to A. So we're working on the same set. Okay, now you might be saying, well, what's the advantage of having a relation on A? Well, it turns out that a relation on A allows us to be able to evaluate certain properties of a relation a little bit easier than if they're two different domains. Now, as you move on in computer science and maybe in other faculties as well, you'll find that there are other relations that are two domains, A to B. But here, we're just going to concentrate on those relations that are relations on A, which is A cross A. So it's working on both of the same sets. Now, the way that we say that there is a relationship between a set A and a set B, or a set A and a set A, is that certain elements are going to be found in the relation. Now, again, earlier in the semester, I gave you an example of this. So if you're not aware of that, please go back and take a look at that example. But whenever we have an element xy that is found in a relation R, it is said to be, it is said to have x related to y in R. Okay, so we say x is related to y in R, and it's usually denoted by something like this. Okay, x, r, y. Now, let me give you a very quick example of this. So there is this relation called a less than or equal relation. Okay, so the less than or equal relation R on Z. Now, remember, whenever we say there's a relation on a set, that means both tuples, both elements of a tuple comes from that set. So here we're saying that we have a relation on the integers. That means both elements of a tuple comes from the integers. So for example, well, to be a little bit more precise, we can say that R is a subset. So notice that this is a subset of A cross B, right? So it's a subset of Z cross Z. Okay, so that is what we're looking at here. Now, let's, in addition, further define this less than or equal to relation. So the relation kind of looks like this. X, Y is in the relation. So R is made up of objects that are in pairs, X, Y, where X is less than or equal to Y. Okay, that is our definition. So you can probably think about a couple of tuples that are in this relation. So I can say, for example, 2, 4 is in this relation. Why? Because 2 is less than or equal to 4. But what about 4, 2? Well, 4, 2 would not be in this relation because 4 is not less than or equal to y, right? So we can similarly say that 3, 3 is in this relation. Why? Because 3 is less than or equal to 3. So understand that these are in the relation because it abides by this definition. Okay. Now, I did also mention that we can denote x, r, y as the element x is related to the element y. So similarly, I can write this, if I've defined my relation r in this way, I can simply write 2r4 or 3r3. Now, certain relations have very special symbols, right? Now, this less than or equal to relation happens to have a very special symbol, which is this thing, right? So instead of writing the r, we can replace the r with the symbol, and we can simply say 2, 4, 3, 3. Now, of course, you all know this, right? Because you've seen the symbol from earlier, but just to let you know that not all relations have special symbols. And when they don't have special symbols, we just use the r in place of that special symbol. Now, a couple of things we should analyze. Actually, before we analyze that, let's do another example. So let's say I have an R, which is xy, such that x is congruent to y mod 5, let's say. Okay, so just in case you forgot what congruency means, we have two definitions for congruency. Number one, we can say that x and y, when they divide by 5, give the same remainder. Okay, that's definition number one. X and y, when divided by 5, have the same remainder. So for example, 12 and 2 would be equivalent, mod 5 here, because the remainders that you get from both 12 and 2 give the same remainder when they divide by 5. Okay, so another definition is that 5 divides x minus y. Okay, so that is the definition of congruency. All right, so keep in mind those two definitions. So now we can, have a few symbols here. So this is our special symbol, right? As I said before, but under this relationship, we can say, for example, 12 and 2 are related to each other. So we can say 12R2. We can say 3 is related to 8. Right, so 3 is related to 8 here, and so on, right? So both of these relations, you can probably think of many, many more that abide by this definition. Now, a couple of things I want to point out right away, and that is that congruency and the less than or equal to relationship are both relationships, but they're actually very different in the way that they approach or the way that they constrain these tuples. Okay, so I'll give you an example. In the less than or equal to relationship, there is order to this tuple. So earlier I mentioned that just because 2, 4 is in the relation, just because 2 is less than or equal to 4, it doesn't mean that 4, 2 is also in the relation, right? Because just because x is less than or equal to y, it doesn't mean that that y is less than or equal to x, right? It doesn't imply that. However, if you take a look at the second relation, the congruency relation, if I say 12, 2 is in the relation, then automatically you can say 2, 12 is also in the relation. Okay, so this is just one property that we're going to take a look at a little bit later, but just note that there are certain relations, and these relations are not made to be the same, right? They have certain properties, and we can evaluate them for their different properties. All right, so let's get into each of these properties. Now, if you look at your notes, you'll see a series of 4 properties that we're going to talk about here. So the first one we're going to talk about is called a reflexive property. So a reflexive property, let R be a relation on set A, then we say X is in A. For all X in A, then XX is in the relation. So what does that mean? That means every object, every element in that set, whatever set you're working on in that set, is related to itself. Okay, that's it. Every element is related to itself. That is the definition of a reflexive property. So, let's revisit this relation on Z, okay, that we had in the last example, and R is the less than or equal to relation. Okay, now for the definition, let's go back, and this is our definition. X is related to y if x is less than or equal to y. So from now on, I'm just going to refer to this as the less than or equal to relation. All right, so what can we say about, now this is a relation on integers, remember, okay? So what can we say about this relation? Is it reflexive? Does it have a reflexive property? So we can analyze. Now, if we're ever not sure, go back to the definition. Is it true that for all x, x is in the relation? Okay, so is it true that x is always related to x in this relation? Well, let's take a look back at our definition. We have x is less than or equal to y. So is it true that x is always less than or equal to x? I think it is, right? So this is true. So we'll say this is reflexive because that for all x, x is less than or equal to x is true. Okay, now sometimes you might have to give a very quick explanation, but I think here is pretty clear. Just remember that anytime there is a property, the property is true, there's usually a mini proof that goes with it, right? So here I would probably say best to do this as a mini proof. I won't write it down, but what we can say is that let's assume that x is not equal to, not less than or equal to x. Okay, and then we can derive the contradiction. So if x is not equal to less than or equal to x, then it must be true that x is bigger than x. And there's your contradiction. Right? So that's it. That's your proof there. And so it is true. And so we say this relation in particular does have a reflexive property. But let's do another example here. What if I gave you a relation let's see, another one that is a subset of z cross z, and let's say R is defined as xy such that x squared is equal to y. Okay, so let's just say this is our relationship. Now notice this is very similar to a function, right? So in fact, every function is a relation first, right? But this is just how we're going to define the relationship. Okay, x and y are both integers, and x squared is equal to y. And that is how we know that it's in the relation. Okay, now again, maybe the question is this a reflexive relation? So let's take a look. Is it true that for all x, x is in the relation? So we're going to repeat this definition over and over again. Now, if we're not sure, let's plug it straight into our definition. That is to say, for all x, x squared is equal to x. Is it true that for all x, x squared is equal to x? Now, what do we mean for all x? Well, for all x, we're talking about this set. We're talking about the set of integers. Is it true about all integers? And no, it's not true. So we can say is not reflexive. And in such a case, it's always best to give a counterexample. So is not reflexive, and we'll say because what can we say? Let's say 3, 3 is not in the relation, and that's all we need to say. Right? It's not true that every integer is related to itself because 3 squared is not equal to 3. It's not in the relation. We're done. Right? So it does not have the reflexive property. Okay, so let's kind of evaluate a little bit here and think about, in general, how many reflexive relations can we have? So in the so let's do it here. So let's give a quick example. Let's say I have set A, which is the set ABC. Okay, now remember what the reflexive property means. It means every element is related to itself. Okay, every element is related to itself. So let's consider A cross A. Now notice here that the size of A is equal to 3. Okay, A cross A. Now maybe you can test yourself. What is the size of A cross A? Okay, so test yourself. See if you can get the right answer. A cross A is this. Okay, AA, BB, CC, AB, BA, CA, AC, BC, and CB. So that is A cross A. That is the set A cross A. Now, if you do a little bit of counting, this says that size of A is equal to 9, or I'm going to put it as 3 times 3. So it's always the size of A times the size of A, or size of A squared. In fact, let's put it as 3 squared. Okay, this will be easier to generalize a little bit later. Now, the question is how many relations, how many different relations are there on A? Now, if you think about it, the definition of a relation, so the number of relations on A. What is the definition of a relation on A? Well, it's any subset of A cross A. I'll say that again. It's any subset of A cross A. So how many subsets are there of A cross A? Well, I know the size of A cross A, size of A cross A. I know the size of A cross A is 9, right? So what's the subset equation? It's 2 to the power of the size, right? So the answer here would be 2 to the 3 squared, 2 to the 9. Okay. Now, if you don't quite remember where the subset equation comes from, let me remind you. Each one of these elements have two choices. Okay, so if I look at AA as an element, if I'm just looking at how many relations are there, then the answer is I either put it into the subset or I don't put it into the subset. There's two choices. It's a 0 or 1, right? I look at BB. How many choices do I have? Two choices. CC, two choices. AB, two choices, and so on. Each one of these elements have two choices. And so that's why it's 2 times 2 times 2, 9 times. Okay, so rewind that if you're unsure, but there's two choices for every one of these elements. And that's why the number of relations is 2 to the 9. Okay, now let's ask the next question. What if I said I want the number of, let's actually do a different color here so we can keep these separate. What if I wanted the number of reflexive relations on A? Okay, so now is a little bit tougher of a question because now we require it to be a reflexive relation. However, I think we have the tools in order to answer this question because reflexive relations on A means that they must include AA or XX. Okay, now in this case, that means our relation must include AA, BB, and CC. So what you're told is that the relation has to have AA in there, has to have BB in there, and has to have CC in there. Can it have more? Yes, it can have other things as well. So take a look at our previous example. I said that the less than or equal to relation is reflexive, right? Just because x is always less than or equal to x. Is it okay that 2, 3 is also in this relation? Or is it okay that 2, 4 is in this relation? The answer is yes, right? Just the fact that x is always related, x is always related to itself, that's good enough for it to be reflexive. So if I had the number, if I have AB in there, if I have AC in there, that's okay, right? It's still reflexive. Okay, so how many different reflexive relations are there? Well, if we include AA, BB, and CC, that means they're already in the relation. So let's forget about them. Okay, I'm going to forget about those three relations or those three objects because they're already in the subset. So what about AB? How many choices do I have for AB? I can put it into the subset or I can leave it out of the subset. Either way, it'll still be a reflexive relation, right? So I have two choices for AB. BA, two choices. CA, two choices. AC, two choices, and so on, right? So, so hopefully you can see that the answer here is 2 to the 6, right? Because there's 6 remaining elements. Now let's see if we can generalize this a little bit and see where this equation comes from. It comes from 2 to the 3 squared minus 3. Okay, now why is it 3 squared minus 3? Because we have 3 squared elements altogether in A cross A. There are 3 elements in the form of XX. Okay, so this is the XX elements. Okay, and this is all of the elements in A cross A. Okay, and those are the only elements in the form of XX. Okay, so I hope that makes sense. So let's move on. Now, in a second, what I want to do is generalize this equation a little bit. But for now, let's move on to the next property. The next property is called a symmetric property. Symmetric property is, again, let R be a relation on A, then XY is in the relation implies that YX is in the relation. So symmetry means that there's no order in the pairs, in the tuple, in the ordered pair. So so let's do an example again. Let's ask the question, does the less than or equal to relation? Now let me just write out the definition again. So xy such that x is less than or equal to y on z, is this a symmetric property? So let's analyze. Is it true that for all xy, that xy in this relation implies that yx is in this relation? Okay, so is it true that if xy is in the relation, that yx must be in the relation? So again, if we're not sure, let's plug the definition straight into our relation definition. So is it true that x less than or equal to y implies that y is less than or equal to x? Well, obviously not, right? So we can clearly come up with a definition here. So we can say this is not symmetric because this is a false statement. And let's come up with a counterexample. We can say that, for example, well, there's many counterexamples. 3 is less than or equal to 4, but 4 is not less than or equal to 3. And that's a good counterexample, and then we're done, right? Because this is saying for every x and y pair that you find, this will be true, and it's not, okay? All right, let's do another example. Let's go back to our relation on Z. So R is this relation, xy such that x is congruent to y mod 5. And let's say this is on Z. Okay, so is this one symmetric? So again, let's go back to our definition. I know it's a little tedious to write it out like this, but I'm going to keep writing it in this way. So is it true that everything, every xy is in R implies that yx is in R? So is it true that for every xy, that x congruent to y mod 5 implies that y is congruent to x mod 5? And again, this is true. This is a true statement. So this is symmetric. Okay, so this is a symmetric relation because this statement is true. Now, again, I said that every time something is true, there's probably a mini proof that goes with it. So again, let's think about what the mini proof would be. I can say that one of the definitions of x's congruent to y mod 5 is that 5 divides x minus y. There's another argument here. There's an argument that says x divided by 5 has remainder r. Y divided by 5 has remainder r. Well, clearly this statement can be switched, right? But let's do a little bit of more mathematical definition here. So this definition implies that 5 times k is equal to x minus y. Okay, so that means 5 times negative k is equal to negative x minus y. And this will indicate that 5 divides y minus x. Okay, this is a very quick mini proof to show you that, in fact, this is a true statement. Okay, so hope everyone is happy with the definition of symmetric property. So I'm going to go back 1 second here, and let's talk about the number of symmetric relations on A. So so let's do a green here. So the number of symmetric relations on A is going to be, now let's think a little bit here, because what is the definition of symmetric again? It means that xy, so x related to y, implies that y is related to x. Okay, so let's split them up into 2 categories. Okay, so I'm going to split all of these parts into 2 categories. I'm going to split them up into the parts where they are xx. And right now, I only want to consider the tuples that are in the form of xy, where x is not equal to y. So all of the ones down here are in the form of xy, where x and y cannot be equal. Okay, so how many of them are there? Well, the short answer is that 3 squared minus 3, many, right? We already talked about this in the previous example. In this example, there are 6 possible relations, or sorry, possible tuples in the form of xy. Okay, there are 6 of them. Now, every time I include AB in my relation, so if this was a symmetric relation and I decide to put AB in there, okay, what else do I need to put in there? Well, I must put BA in there. To keep it symmetric, every time I put XY, I must put YX as well. So that means that even though I have a choice in putting in the tuples, these two, BA and AB, belong together. So this belongs in one group. Okay, so this is one group. What's another group? Well, another group would be BC and CB. If I decide to put one in there, I better put both in there. Okay, another one would be CA and AC. Okay, so this one and this one. Right, that would be another group. So how many groups do we have altogether? We have 3 groups. Where does the equation 3 come from? Well, it comes from the fact that we have 3 squared minus 3 of these xy's, right? So we have 6 of these xy's, but we can only use half of them. Okay, so say that again. We have 6 of these xy's, okay, 6 of these element pairs of the form xy. I can only use half of them because everything is paired off. Okay, it's paired off as AB, BA, right? That's one pair. CA, AC, that's another pair, and so on, right? Okay, so this is one part of it. So I'm going to have 2 to the power of this, okay? Now, we're not quite done because I did leave out the xx's. Now, how many xx's are there? There are 3 of them. Now, would you agree that if I wanted to make a symmetric relation, so let's say I decide to put AB and BA in there. I also decide to put CA and AC in there. Now, your question might be, do I have to include BC and CB? The answer is no, I don't, right? If I don't include it, it's still symmetric. The definition of symmetric says if I see XY, then I see YX, right? If I see XY, then I'll see YX. But if I don't see XY, I don't need to see YX. If I don't see BC, I don't need to see CB. Okay, so that's why those groups that I just circled, they are optional. They are all optional. Okay, what if I decide to put AA in there? If I put AA, for it to be symmetric, what else does it need to be? Well, AA also needs to be there. So do you agree that AA as itself is one group? BB in itself is one group, and CC in itself is one group. Now, please keep in mind here that we are not talking about reflexive. We don't need to include those 3. Okay, we don't care about reflexive. We're only talking about symmetric here. So understand that AA, BB, and CC are in themselves groups. So I can include them if I want, or I don't need to include them if I don't want to. So there's my full equation. 2 to the 3 squared minus 3 over 2 times 2 to the 3. Now, since we can combine these two, we can actually very quickly combine them and get 2 to the 3 squared minus 3 over 2 plus 3. Okay, so now I know this equation looks a little bit weird, but what I want to do next is try to generalize everything. Okay, so let's generalize this equation. So I'm going to use a black this time. So instead of the size of A being 3, let's assume now that size of A is equal to n. So let's answer each of these questions again. What is the size of A cross A? Well, the answer would be n squared, right? 3 times 3, n times n. How many relations are there? Well, we said it's just 2 to the power of 3 squared, right? So this would be 2 to the power of n squared. That's how many relations are there on A. Okay, what about the reflexive relations? How many reflexive relations are there? Well, we found all of the objects here that are in the form of xy because those x's are already in the relation, right? So we ended up with 2, 3 squared minus 3. So in general, it's going to be n squared minus n, right? So if you imagine that we have A, B, C, D, all the way up to n elements, then there's going to be n squared of them, but there's going to be n in the form of AA, BB, CC, all the way up to the nth element, right? So we do n squared minus n. Okay, the last one. How do we analyze that? Well, we said the equation is 2n squared minus n divided by 2 plus 3. Yeah, sorry, plus n. So similar argument here. We have 3 squared minus 3 of those xy's. I divide it by 2 because they're all going to be paired off. And then I have n individual x's, so I add them as well. Now we can do a little bit of math at the top of this, and we should get something like 2n squared plus n over 2. So please check my math. Please check that those two are actually equal. But that's the equation. So try to remember these because they might be very helpful, especially when we're counting relations or when we need to count a relation or when a particular counting problem is nothing more than the number of relations. Okay, so before we end off this video, let's do one more property, which is called the transitive property. So the transitive property is for all x, y, and z. Okay, so this is a statement on for all y, x, y, and z. We want to know, we want to say that x related to y and y related to z implies that x is related to z. So that means this is kind of like a skip the middle one, right? So x skip the y can directly go to z. Okay, so let's go back to the two definitions that or a couple of definitions that we know from before, and let's analyze those and see whether we understand this property. So what about the R is xy such that x is x is less than or equal to y, and this is the relation on the set z. So what about this? Is this a transitive property? So let's plug it into our equation for all x, y, and z. If x is related to y and y is related to z, then x is related to z. So is that a true statement? I think it is, because x less than or equal to y is less than or equal to z. This will guarantee that x is less than or equal to z. So this is transitive. Now, again, anytime we say that it does have that property, let's think about a mini proof to go along with this. So let's pretend that we have y minus x as a positive integer. Okay, so y minus x is a positive integer, p. Or sorry, not positive, non-zero. Okay, so non-zero, we'll call it n. Z minus y is also a non-negative number. So it can't be negative, right? Just because x is less than or equal to y and y is less than or equal to z, when I subtract these two numbers, they must be non-negative numbers. Okay, so let's, how do we do this here? Let's add these two. So if I add these two, I'm going to get z minus x is going to be n1 plus n2. Now, if you take two non-negative numbers and you add them together, you will also get a non-negative number. Okay, so it's a good mini proof. This is always good practice for discrete mathematics to kind of think about how you would prove this to be true. Okay. All right. So let's do another one before we end off this video here. And let's do another relation R on Z. And let's define this R as we'll call it AB this time. AB such that A times B is greater than or equal to 0. Okay, and this is a relation on R. Now, since we know 3 properties already, let's analyze it for reflexive, for symmetric, and also for transitive. All right, so what about reflexive? Okay. Can we say that for all x, x times x is greater than or equal to 0? So is it true that for all x, x squared is greater than or equal to 0? Yes, this is true. There's a mini proof for that because you can graph it or you can do anything like that. Okay. Is it symmetric? For all xy, x times y being greater than or equal to 0 implies that y times x is greater than or equal to 0. Well, yes, because there is a associative property to multiplication. Saying that x times y is greater than or equal to 0 is really saying the exact same thing as y times x is greater than 0. So that's very, that's very intuitive. It's very obvious. Okay, transitive. For all x, y, z, is it true that if x times y is greater than or equal to 0, y times z is greater than or equal to 0? This implies that x times z is greater than or equal to 0. So now is probably a good time to just pause this video and try to think about it for yourself. Is it a true or false statement? Now, if it's true, there is a mini proof that goes with it. Okay, so can you prove it kind of on the side? You can just kind of think about it. Can you prove that this is going to be true? If not, there must be a counterexample that goes with it. So can you give a counterexample in which the thing before the arrow is true, but then the thing after the arrow is false? Okay, so you can try that, but let me give you the solution. It's actually false. Why? Because there is a counterexample that goes with it. So the counterexample is, let's say that I have 1 times 0. So 1 times 0, everyone would agree, is greater than or equal to 0. And then I can do 0 times negative 1. Everyone would agree this is greater than or equal to 0. But does this imply that 1 times negative 1 is greater than or equal to 0? No, this does not imply that. And there is our counterexample. And we can say, therefore, this is not transitive. Okay, so so that's it. That is our definition of the 3 properties. All right, when we come back in the next video, I want to talk about another property as well as going a little bit further with defining what these properties actually look like visually. Okay, so I will see everybody in the next video.